Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The title of my talk is not terribly original here. We all have lots of reasons to thank Butler. The whole world has lots of reasons to thank Butler. But you already know what those are. So this is a personal thank you of what I have to thank Butler for. First, a little bit of introduction. This is me, Lamport. This is Butler, Lampson. Now, I realized there was some confusion about this when someone sent me email mentioning my Turing Award lecture. So you should learn to distinguish us. I'm the one with the beard. Butler is the one with the Turing Award. Okay. Now, I met Butler sometime in the early 70s. We can't figure out when. And in 1977, I interviewed at Park. I wanted to join all those brilliant, wonderful guys who were doing these wonderful things. And I gave an interview talk, and in it, I said, a fault-tolerant distributed system must use real time, otherwise it can't tell a lost message from a slow one. And I knew I was just hand-waving. You know, it sounded reasonable, but you know, it was just very informal. Now, Butler has a habit of going to sleep during a lecture. Someone forgot to turn the counter on. I guess that gives me a couple of more minutes. Has a habit of, quote, going to sleep during a lecture. Of course, he's not really asleep. And then at some point, he will open his eyes, raise his hand, and ask a question that completely demolishes what the speaker was saying. So I don't actually remember whether Butler had his eyes closed during my lecture there in 1977. I see his eyes are open now. That's good, a good sign. And he did raise his hand and say, bogus. Well, in those days, people didn't say bogus, but what he did say is that he said, he pointed out that I was just waving my hands. And this motivated me. And a few days later, I sent Butler an email with a proof of that, which unfortunately I still don't have anymore. But it wasn't really a rigorous proof, and it wasn't very good, and I just forgot all about it. Well, fast forward to 1985, and this paper by Mike Fisher, Nancy Lynch, and Deb Patterson, Impossibility of Distributed Consensus with One Faulty Process, the famous FLP paper. And like everyone else, I was completely blown away by its elegance and the generality of its result. So thank you, Butler. You pointed me in the right direction, but I just wasn't smart enough to get there. And perhaps it was because of that I wasn't wasn't smart enough for the work at Park, that I didn't get the job. So instead, I went to SRI. And actually, that turned out to be a pretty good career move. I worked on Byzantine generals. I did LaTeX. Of course, if I had been at Park, maybe I would have done it worked on Bravo, and maybe instead of coming here from California, I would have had to come down from orbit to get here, but that's another story. So I don't know if you were responsible for my not getting the offer, but if you were, thank you. It really worked out well for me. Then in '85, I moved to, many of the people from Park moved to Dex Circ, and I moved there too. I don't remember if Butler was even at my hiring talk, but I talked about snapshots, and maybe photography is one of the few things that Butler doesn't know a lot about, but he did not raise any objections, and I did get the job. So Butler at DEC. Circ was in Palo Alto, and the DEC engineers were in Marlboro. And time to time, Butler would go back and talk to the engineers there. And the story that I heard was that Butler would spend a day at Marlborough, and that would leave the engineers with enough to do to keep them busy for 6 months. So on behalf of the DEC engineers, thank you, Butler. And while I was at CERC in 1989, I discovered or invented the Paxos algorithm. Now, I thought that was an important algorithm. And one thing I learned from Dijkstra, in particular from his dining philosophers problem, which became very famous, is that the way you get people's attention is by having a cute story. So at SRI, Marshall Pease and Rob Shostak had developed some idea which they called interactive consistency. And my biggest contribution to this whole business was changing the name from interactive consistency to Byzantine generals. And indeed, that did get people's attention. So when I discovered the Paxos algorithm, I decided to make a story. I wrote this story about a Greek island and where people had pseudo-Greek names, which were actually the names of computer scientists. And this was a total disaster. People got hung up in the names, tried to read them. Nobody paid any attention to what the paper actually said. So no one paid any attention to that algorithm, except Butler. Now, I don't know, perhaps Butler paid attention to because of the paper's ending, which I see from his laughter that he does remember. And this was the very end of the paper. A general named blah, blah, blah established a military dictatorship. Well, for those of you who are not fluent in Paxon, this was the latex source of that ending. So perhaps because of that, Butler told everyone to use Paxos to build reliable distributed systems. And they listened to him because he is Butler, and people are smart enough to listen to Butler, and that's what they do today. So thank you, Butler. Well, meanwhile, actually a year earlier, Brian Oakey and Barbara Liskov published a paper called View-Stamped Replication, blah, blah, blah. I don't remember the complete title, but and they presented that at SOSP in 1998. And Butler, together with Bill Weil, discovered that Paxos and view-stamped replication were in fact the same algorithm. So when Barbara invents something neat, she builds a system. When I invent something neat, I make a story. And I'm sorry, Barbara, but even a bad story beats a good system. And so the algorithm is known today as Paxos. Okay, go ahead to Naples in 1995. I was invited to give a talk at some conference that marked the 150th anniversary of some kind of famous scientific congress that had happened in Naples. And I don't remember exactly what the details of it were. But for a 15-minute talk on the future of computing, blah, 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 nothing to say. My wife and I were flown business class to Naples. We stayed at a 4-star hotel. We were entertained for a week and had a lovely time. Well, the night we arrived, we were invited to dinner by our host, who was the head of the computer science department, who was the one who was responsible for inviting the computer scientist. And in the course of dinner time conversation, as he was serving the drinks, here's what he said. Thank you, Butler, for a wonderful vacation. Okay. So why have I been invited? I'm given the great honor of talking at Butler's birthday party. Well, so I've worked sort of at the boundary of theory and systems. And there's a wonderful thing about doing that. You see, the systems people would say, boy, for a theoretician, this Lamport guy knows quite a bit about systems. And of course, the theoreticians would say, well, for a systems person, this Lamport guy knows a lot about theory. Well, unfortunately, I really couldn't keep that up for very long, and couldn't even convince the theoreticians that I was a systems person. But people will still say, for a theoretician, Lamport knows a fair amount about systems. So how do I still fool them? Well, secret of my success, in the words of Igor Stravinsky, or in the words of Lobachevsky, plagiarize. And my knowledge of systems has been stolen from two people. There's Butler and our late lamented Jim Gray. So thank you, Jim. But thank you, Butler. An example, in December, there was Butler talked at a birthday party for Fred Schneider. And because of that talk, I'm now telling people about retroactive security. So thank you, Butler. Now, this being a birthday party, I actually have a birthday present for Butler. It's on a memory stick here that I will give to him. Now, Butler needs it because he now describes algorithms in what I regard as a form of pseudocode. He calls it spec. So what's wrong with pseudocode? Well, there are two things wrong with pseudocode. First, it's pseudo. So what's wrong with that? Well, you can't check it. And why do you need to check it? Well, for reasons that I've actually forgotten. About 10 years ago, I Googled, there wasn't any Bing then, quicksort, and tested the first 10 algorithms that I found. Half of them were correct. Every one not written in executable code was wrong. That is, the ones that were correct were only correct because people had debugged, they were written, had executed, and they were debugged. And what else is wrong with pseudocode is that it's code. If you're talking about algorithms, you shouldn't be thinking at the code level. You should be thinking at a level higher than the code level. And it's hard to think about the code level when you're writing code. So the replacement I have for pseudocode is called PlusCal. It looks like a toy programming language, but an expression in it can be any mathematical expression. And the PlusCal code gets compiled into a TLA plus specification. And you can model check it. And you can get a grad student to write a completely formal machine-checked correctness proof of it. It's not something you're going to want to do yourself, Butler, as I think you realize. And I'll just illustrate it with an example. This is a paper. Don't ask me what this paper is about, even though I'm an author. Well, I do it. No, a bit of it. It's a real lily pure theory paper. And I have no idea why people should be interested in this. My job in this operation was, I was the formalizer for this paper. And I don't know, people know Ellie Gaffney. He's a wonderful guy, really smart, but he is no fan of formalization. I don't think he's, he hadn't, before he saw PlusCal, he hadn't written anything formal in his life, as far as I know. But when he saw the PlusCal algorithms that I wrote to this, the PlusCal version of these algorithms in this paper, he was really blown away by how elegant it was. So I'll just show you one of them. It's the simpler one of the algorithms. This is what it looks like when you use the tools, and our our IDE. This is what the pre-printed version of it looks like. This is the simpler of two algorithms. And the algorithm appears as a comment in a TLA plus module. And don't try to read it. I just want to point out, just one little thing about this. Well, it declares proc to be a constant, which is going to be a set of processors. And you can see that there's a process declaration. So this says it's a multi-process algorithm with one process for each element in proc. It has labels. To specify a concurrent algorithm, you need to specify the grain of atomicity. And in PlusCal, this is done in a really neat way with labels. And an atomic action is an execution from one label to the next. And now I want you to just look at this. There's a declaration of a variable A1. And what it says is that A1 is the initial value, it gives you its initial value. And it says it's an array indexed by natural numbers. And for each I, A1 of I is initially the empty set. So that's what little piece of TLA plus notation. It's what most people would write with a lambda notation, but lambda has so overloaded with other stuff that I invented a new different notation for TLA plus. Anyway, and here's an assignment statement. It says known, this variable known, is equal to known, and the union of this expression. Well, what is this expression, n union of A1? Well, it's defined here. And what that does is it defines n union of A1. A1 is an array indexed by natural numbers. So it's the union of this infinite number of sets, A1, 0, A1 of 1, et cetera. And that's just a typical statement in a PlusCal algorithm. We're not at the code level anymore, Toto. You're viewing this as really abstract. It's math. It's really great. But you can debug it with the model checker. And what I did is I wrote machine check proofs that it implements its specification. And its specification was also written as a PlusCal algorithm. So Butler, I've been trying for years to get you to use TLA plus. So this present may be as welcome as a Christmas fruitcake. But like a Christmas fruitcake, you can re-gift it. And unlike a Christmas fruitcake, you can re-gift it as often as you like. So here is PlusCal on a memory stick. And just read the HTML file. OK. And thank you all.
All right, time for questions.
Your example had a go-to in it.
Hold on. You want to?
It turns out go-tos are harmful in programs. Everything you've learned about programs, most of it doesn't apply to specifications or to algorithms. Go-tos are bad because programs are complicated. But when you have something that's really nice and simple like that, a go-to isn't a problem. And in fact, it can make it, I wrote it with a go-to, not because I had to use a go-to, but because it was clearer with a go-to.
More questions, anyone? We're fading towards the end of the day. So let's thank Leslie again.